The work presented here was developed by Milton J. Lopes, student at the Systematized and Software Development course, in collaboration with Dr. Daniele Araújo Luna at the University called Instituto Federal do Triângulo Mineiro in Brazil. The following work is entitled Using Cellular Automata in Path Planning Navigation Control Applied in Surveillance Task through epoch Architecture. It's a research that deals with the use of cellular automata and path planning and has as a central point a task of monitoring an environment. And this work needs to describe three key points. Within these key points are how the implementation of the algorithm can influence its real-world performance. And the second key point that's going to be answered here is how the design of cellular automata can be used together with this algorithm and how it's going to influence the code implementation. And the third key point is how the integration of both approaches, implementation and cellular automata, can be prepared for real-world applications through testing in a robotics simulator. Robotics, being able to solve a wide range of problems from mass production to exploration of hypospite environments, can also solve problems of surveillance. And since surveillance is a key task, in combination with cellular automata, it allows the discretization of the proposed system with a modification of the A-star algorithm and its integration with cellular automata with application in surveillance. So, as the main objectives of this paper here, we have the monitoring of an environment through the optimization of an A-star algorithm, and the use of two heuristics in combination with cellular automaton. Also, we are going to make graphical visualizations of simulations here, and we also are going to analyze the results in the VREP simulator. The proposed model was a discretized navigation model based on a cellular automata, and it also has the contribution of an algorithm optimization. Specifically, the A-star algorithm is going to be a bit modified here, and this work also presents a simulation of the model navigation. First, we divide the environment into squared cells, which is the automaton, the cellular automaton, and our robot starts at the position xig. For expanding the nodes as the pathfinding task is done, it's used a more neighborhood and a von Neumann's neighborhood and two types of heuristics. So the main objective is to find how the combination of those factors can influence the final results. As a methodology for the A-star algorithm optimization, a code profile was used for profiling the code. The modification of the A-star algorithm was the replacement of a list with a matrix data structure, and this small modification makes the complexity of nodes expansion task to lower from O of n to O of 1. This helps us to achieve much faster results when it's about the path planning task. For the model navigation in the VREP, there are a number of factors to be considered, and in this case, the VREP remote communication API was used to control the puck robot. A compass and a GPS have been added to the robot, and the cellular automaton coordinates are then transferred by the remote API. In the compass's informed angle and GPS position must be considered to allow those coordinates to be transformed. As a methodology, we have used the number of 7,500 simulations for the robot navigation, and implementation was done in the C language with the STL graphics library. The code profiling was using the new gprof tool. Also, it was done a visual analysis, and combining the neighborhood expansion and the heuristics used to calculate the cost of the path planning, we have made 8 different combinations, and tested which was more optimized for solving the problem. The experiments were divided into 3 main blocks, where the first displays an experiment block analysis. 2 environments are tested for the surveillance task using a standard C language implementation with the STL Simple Direct Media Layer graphics library. Subsequently, a set of 7,500 simulations are made for each of the environments that will be demonstrated. And finally, experiments are done in the ViewRep simulator using the epoch architecture, showing that this task can be used in a simple architecture. Figure 2 shows an environment of size 20 per 30 cells, and it shows that 6 homes must be monitored by the robot controlled by the CA. So there is a transition row, and this transition row is based on an A-star algorithm that has been optimized and integrated with the CA. We have these environments, and these environments specifically have 6 homes, and it's testing 2 types of neighborhood with 8 and 4 cells. For the visual, also in the chunk of visual analysis, in the same way, figure 3 shows the home 2, also 20 per 30 cells in size, where 7 homes are covered. And from the analysis made here and counting the number of cells traveled, we conclude that the heuristic which finds the best route for environment navigation is the one that explores an 8 cells neighborhood. For a more accurate analysis, consider the number of cells explored in border cells. A detailed statistic was made, and it's going to be demonstrated in the following items. This is an analysis of runtime and function calls, and here to compare the implemented algorithms versions. Some analysis of results are presented in terms of CAD functions and time spent, and in this figure the 8 different combinations can be seen in order, analyzed through 7,500 simulations per combination per home. You can also see that type 4 is faster in terms of processing. However, the shortest path is the one that uses Moore's neighborhood and Euclidean heuristics. This means that it takes about twice as long to find the shortest route as compared to type 4, which is faster. Also, in the analysis of runtime and summary, this figure shows the level comparison of complexity for the environment in figures 2 and 3, and the environment in figure 3 represents the critical levels of processing time in relation to the environment shown in figure 2, taking into account 7,500 experiments. Here, the final changes are observed in this case in relation to function calls. And we can notice here that most of the time the processing times follow the same pattern in relation to the experiment that present the function calls. As a simulation using the epoch robot that you can see here, we have an implementation of the model performed using different combinations of heuristics and neighborhood exploration, adding some features and elements that allow navigation in the environment to be completed. Initially, the VRAP simulation environment is set up and the epoch robot is fitted with a capacitor GPS, and this allowed for the necessary feedback to perform the test. In addition, the environment was configured so that the 7 cm size robot could fit in the trajectory, and so thus we have for each cell a size of 14 centimeters. Here are the results of the VRAP simulation, and about this important configuration, the thing is that the addition of virtual obstacles, which avoids collision of robots with real obstacles with 90-degree angles, and also the robot can rotate, as can be seen in the previous simulation, and in this axis we can see the execution of the movement of the monitoration. So basically every robot is going to move at a position closer to the center of the room, and it's going to rotate by 360 degrees, and then it's going to continue and repeat this pattern until it can reach the final position. In this work, we investigated a new model of robotics and navigation in the surveillance task. Regarding our improvement in the optimization of the A-star proposal, our results showed a considerable increase in the final algorithm. As future work, we can make other improvements to A-star, improving the quality of search in the environment.